This video is going to teach you everything you need to know from section 7.2 for your quiz on Friday. It's going to involve sectors and arc lengths of circles and computing those in both degrees and radians. Here are the formulas that you learned back in geometry for the area of a sector and the arc length of a circle. Now we need to look at what happens if our central angle is measured in radians. So if we try to derive these radian formulas and transfer the ones from degrees to radians, there's a few different ways we can do this. I'm going to stick to converting because that's what we've been talking a lot about. First thing I'm going to do is draw in the degree symbol, so we have our units here. I'm actually going to start down the bottom with arc length. All I'm going to do to convert, we need to get rid of that degree symbol. So if we multiply this by 360 over 2 pi, we can also do 180 over pi or any other conversion that we know. What happens here when we start to cancel things out, the 360 degrees are going to cancel and the 2 pi's are going to cancel. What that's going to leave us with here is S equals R times theta. The other way we could derive that is from the first formula that we learned when we were talking about radians and how to make those angles. If we solve for S here and just multiply by R on both sides, we would end up with the exact same formula. So there's two different ways to do that. The easier one is probably just moving around this formula, but I wanted to show you the conversion because that's what we're going to do for the area formula as well. So if we take a look at that and do the same strategy, multiply by 360 over 2 pi, our 360's cancel again. One of our pi's cancels. We still have a 2 on the bottom there. And this equals, and if I clean this up a little bit, we get 1/2 r squared and theta. So that's one of our formulas. There's actually two different ways that we can look at the area formula for radians. If I write this out and just expand the r squared as 1/2 r times theta, well, what you'll notice here is r times theta we know is S. Well, we have an r times theta here. So another way you can write this formula is by substituting this in, taking this expression and subbing it in here. Putting the S in there, we get 1/2 RS. So there's really two formulas for the area of a sector. You can derive those either way. And then there's one formula for the arc length. The next slide is going to sum this up in a nice little chart for you. I know this got a little bit messy. So here's what we have. Here are all the formulas that we just talked about. You may want to kind of put them in a chart or some organized fashion in your notes so you can refer back to them. On the next few slides, we'll do a couple practice problems, and that'll be it for 7.2. I'm going to change this example slightly and make this 45, 25. So a sector of a circle has an area of 25 square inches. We know that K is 25. We're looking for the central angle and the arc length in radians if the radius is 4 inches. So we know that R is 4. Anytime I have K and R to work with, I prefer to use the 1/2 RS formula. So if I do that, I get 25 equals 1/2. R is 4. We're looking for S. So we end up with 25 equals 2S, or S equals 25 over 2, which is 12.5 inches. So there's our arc length. Now we need to go back and find out the central angle. So again, I would go to this formula, theta equals S over R, kind of the most simple one we have. The theta is what we're looking for. We just found that S is 12.5. We know that R is 4. If I plug that into my calculator, I end up with a central angle of 3.125 radians, which we know is really close to pi because pi's approximation is 3.14. So there are our final answers. We get an arc length of 12.5 inches and a central angle of 3.125 radians. As you read through this next example, the one word that should jump out at you is degrees. We haven't seen any with degrees yet, so we will be using those formulas with the thetas in them. So a sector of a circle has an area of 64 square centimeters, so K equals 64. We're looking for the arc length, and we know our central angle is 43 degrees. Since we only have the area in theta, we need to use theta over 360 pi r squared. We know that's the area formula, so we can plug in 64. Sorry, we know theta, so I can plug that in. So this will actually look like 64 equals 43 over 360. And we're trying to solve for r. When you plug that in and try to get r by itself, you end up with a radius of 13.06, and we're in centimeters again. So 13.06 centimeters is our radius. We were asked for the arc length, so this is really a two-step problem. We couldn't get to arc length in one swipe. But now we know that the arc length, and again we're in degrees, so we can only use those formulas, is theta over 360, 2 pi r. Now we have enough to solve that, so we can say the arc length equals 43 over 360, 2 pi, and we know our r is 13.06. And again, on your calculator, you'll come out to an arc length of 9.80 centimeters. So again, two-step problem to get to where we need it to get to, but not too bad. We only had to use two formulas. Just be careful of radians and degrees. That trips people up a lot. There's one more type of problem in this section. This one's definitely the hardest. It says find all radii, which means there could be more than one, of a sector with an area of 15 square units and a perimeter of 16 square units. The hint here for any time you see these problems with area and perimeter, you want to use our radian formulas. So we're going to do these in radians. So we know already that 15 square units is our area. That's going to be equal to 1/2 RS. Again, anytime you can use this formula, you should. Perimeter is a little bit trickier. If we think about a sector of a circle and its perimeter, we know that the sector has 2 radii and also the arc length. So your formula for perimeter that you can use for all of these is 2r plus s. So our equation for that can say that 16 equals 2r plus s. Since we have two equations, this ends up being a system of equation. Nice flashback to Algebra 2 for you. I think the easiest way to approach this is to solve for s here and use substitution. So this formula becomes s equals, and then 16 minus 2r. What we're going to do with that is take this expression and plug it into our area formula and for that s. I take that over here, we end up with 15 equals 1/2 r times 16 minus 2r. If you distribute the 1/2 r, you end up with 15 equals 8r minus r squared. Since we have that r squared term and also a linear term, these are always going to end up being quadratic equations, which hopefully you can factor. If not, you can always use a quadratic formula. I know before I can factor, I need one side to equal 0. Since this r squared is negative, I'm going to move everything to the left. So I end up with r squared minus 8r plus 15 equals 0. At this point, when I try to factor, I know we end up with r minus 5 and r minus 3. So my possible radii here are 5 and 3. That means that there are two possible circles where the area can be 15 and the perimeter can be 16. Excuse me, two possible sectors where that can be the case. These are definitely tough problems. You may need to use the quadratic formula, remember, if you can't factor, but we definitely need to brush up on factoring in order to do these. There are 3 of these on your worksheet and 1 more on the review sheet before the quiz, so you should get plenty of practice and be able to get these down.